So oftentimes when we have combustion reactions, so this is where we're going to have the burning of fuels. So anytime we burn organic molecules, they're going to react with oxygen gas, and they're going to release carbon dioxide and water if they burn to completion. So let's try ethyl alcohol as our burning substance. So ethyl alcohol is also grain alcohol, so it's the alcohol you would be drinking in your beer or your wine or hard liquor. So this is the alcohol molecule, written just in its molecular formula. It's actually put together a little bit differently than that order. But that's going to react with our oxygen, and it's going to yield CO2 plus water. So these are always going to be the products of a complete burn of our hydrocarbons. So again, there's lots of energy that are held in carbon-hydrogen bonds, and when you burn the material, you're ripping all of those guys off and you're releasing that energy as heat in the case of burning something. If we were to drink this and have it be metabolized in the body, our bodies would do essentially the same thing through the Krebs cycle inside the mitochondria to make ATP molecules. It would actually be using that ethanol to create energy. And actually there's quite a few calories in ethanol. So do you know how many calories there are in carbohydrates and proteins? So carbs and proteins, there's about 4 calories, big calories, so they're actually kilocalories per gram. And fats and lipids, there are 9 calories per gram. And for ethanol, or grain alcohol, there's 7 calories per gram. So alcohol actually has a lot of calories, so you shouldn't drink too much because you can gain weight by drinking lots of beer. Okay, so in our combustion reaction, back to our reaction, we're just going to light our ethanol on fire, and it's going to react with the oxygen, release carbon dioxide and water. So to balance this guy, we can see that we've got carbon, hydrogen, and oxygen on this side. Still have carbon, hydrogen, and oxygen on this side. So we've got 2 carbons on this side, 1 carbon on this side. We've got 1, 2, 3 oxygens on this side, and that's arranged in a 1 plus 2 fashion. So we can move these around independently. Maybe we're going to try to get that guy even. And how many hydrogens we have? 6. And we've got 2, 3 oxygens on this side, and then 2 hydrogens. So I still feel like we're going to need to make our oxygens be even to get this guy to work. And so what I'm inclined to try first is to even up our oxygens by just multiplying that by 2. So if we do that, we change our oxygen concentration to now having 4. And we change our carbon concentration on this side to having 4. And our hydrogens to having 12. So now let's see if we can balance the carbons and hydrogens on this side and then fix any oxygens we have left over on this side. So if we have 12 hydrogens, we've only got 2 on this side. That's an easy change to get the 12. Just multiply it by 6, right? That would give us the 12 hydrogens, and that would end up giving us 6 oxygens. They don't match yet, but we're not concerned. We've got the extra oxygens over here to deal with. And let's see, how many carbons do we got? We have only 1 on this side. We have 4 on that side. So if we change this to 4, that changes our carbon to 4. And now it's going to change our oxygen again too, because we've got 8 plus 6. So that's going to be now an oxygen total of 14. Okay, so now what do we got on this side? We've got balance between carbon, got balance between hydrogen, and now can we balance the oxygen? And then we'll take a look and see if we can have better balance at a lower level, like if we can reduce all of our things. So right now we've got 2 oxygens with this guy, and we don't want to change that one. So 2 of the 14 are going to come from this molecule. That means 12 of the rest have to come from this. So we're going to need 12 more. We can get that by placing a 6 out in front here. And that's going to give us our 14 oxygens. So now we're balanced with our equation written as this, in this way. But this is not the lowest form, is it? So I lied and said we had to double this, and we really didn't. So if we divide everything by 2, we should get the lowest common denominator. So we've got C2H6O plus 3 O2s. If we divide this one by 2, 2 CO2s plus 3 waters. We double check and make sure that this is still right. I've got 2 carbons on this side, so now my carbons 2. We've got hydrogen. We've got 6 on this side, and our oxygens 1, 7 on this side. So let's see if we have the same on the other side. Carbons are going to be 2. Oxygens are going to be 4, 5, 6, 7. And our hydrogens are going to be 6. Those guys match. So this is our best balanced equation up on the top. So you always want to have the lowest common denominator be the way that you balance the equations. And so again, it may take a little bit of work to get to the correct balancing or the correct formulas. But eventually, you're going to get it down and you're going to work it out. So those are just some examples balancing equations. In the next set of reactions that we'll go over, we'll actually look for recognizing and putting together double displacement reactions, so both precipitation and acid-base neutralization reactions. And then we'll also take a closer look at redox reactions as well.